just kind of come at me, I guess, in terms of practice, where I'm looking at large sediment injections into river systems. This one is one of the more interesting stories I've run into there. I think that'll become apparent why. So let's get started. Join me on a journey across the Pacific Ocean to the north edge of the Cascades Volcanic Arc and into the Lillooet River Valley, where the Lillooet River has filled a glacial lake fjord with sediment from Mount Meager, a glaciated stratovolcano that's hydrothermally decomposing and releasing a very large sediment yield with a particular event that we'll look at here. That sediment moves down the Lillooet River, a steep braided cobble gravel river, which transitions through a wandering reach here into a lower gradient reach surrounded by agricultural and urbanized land that's protected by dikes. In 2010, the Capricorn Creek landslide mobilized nearly 50 million cubic meters of sediment off the north flank of Mount Meager, making it the largest slide in Canadian history. That came down to the Capricorn Creek Valley, crossed Meager Creek, and actually ran up about 700 meters on the slope here, and then continued down and deposited a mass of sediment, walking both Meager Creek, which is coming at you from the middle of the slide, and the Lillooet River coming in from the right. This represented about 75 years of the typical, already very high annual sediment yield for the Lillooet River system. It dammed the river and Meager Creek, the tributary here, but the dams didn't fail catastrophically. They overtopped shortly after this slide, and channels subsequently have incised through the slide deposit. The motivating factor for the chance that I had to get out and look at this story was a flood hazard study completed downstream, and the managers of the river system and flooding conditions there rightly wondered, well, given this event that happened in the headwaters, how does that affect the flood hazard picture and challenges that we may have regarding managing this river? So our focus here is really, how did material from this landslide enter into the Lillooet River and move downstream? What are the processes driving that, and how do those relate to flooding conditions? Key questions that guided that investigation were, how much material of what kind is eroding from the slide deposit? And implicitly in that, how much material is still to erode, and how fast might we expect that to happen? Where is that material going? And how is it affecting the channel morphology and hydraulic conditions and flooding conditions? So first, focusing in on that first question. How much material of what kind is eroding from the slide deposit? The answer is a lot of different things. Here, I just need to make sure to emphasize the scale. These are fully grown trees. The river's eroded tens of meters through the landslide deposit here in Meager Creek, mobilized a very large volume of material. That material consists about 60% of the lithology that you see in this picture in the top right, which is a very distinctive porphyritic dacite that's not present elsewhere in the basin except coming off Mount Meager itself. And so that material proved a really useful tracer to see where the slide material is dispersing downstream. To estimate how much material is eroded out of the landslide, we combined satellite photogrammetry from shortly after the event with LiDAR collected about 5 years later to understand over that first 5-year period, we're 5 years on from the LiDAR data now, how much material had eroded out of the landslide. We also added in a couple of other factors to account for the channels that you can see already eroding into the slide here in the satellite photogrammetry from shortly after the slide event, and based on areas that we see the channels migrated laterally since 2015 into the terraces. There's also going to be some factor of degradation in the channel, but we don't know what that is because we don't have recent full topographic surface of the landslide. We looked closely at that material and did bulk grain size sampling of it to determine that it consists of about 20% silt and clay, about 37% sand, about 40% gravel, and about 3% boulder-sized material. The boulders, for the most part, have stayed in place on the slide deposit and not been moved by the rivers, where the gravel, sand, silt, and clay are dispersing downstream in variable distances. Here we can see how some of that material is moving downstream using the gravel sizes as a tracer, in particular that porphyritic dacite and andesite that's indicated in the red. We were able to compare our observations of the bed material lithology against a data set that had been collected prior to the landslide deposit and show that there are substantially elevated quantities of the volcanic material that match where we see this material that's coming directly from the slide along much of the upper portion of the river, particularly down to about river kilometer 55 here. In that upstream reach that's mostly impacted by gravel size fractions from the landslide, we see three key geomorphic or morphodynamic impacts. We see that the bed material has gotten a lot finer, and we infer from that sediment transport rates have increased markedly. We see the channel widening substantially, and we see all sorts of indications of major aggradation, including sedimentation on the floodplain, kill of trees due to elevated groundwater levels, and formation of avulsions. The figure in this slide is taken from a geomorphic atlas I prepared, systematically mapping geomorphic conditions along the Lillooet River that I'll share a link for at the end of the presentation, just a plug for that. First, we'll look at how the grain size distributions have changed along the river. Starting upstream in the red plots with the dashed line indicating the grain size distribution from 2001 and the solid line indicating the grain size distribution from 2017, we can see a major increase in the proportion of sand characteristic along all of these sample sites and major decreases in the median grain size, or the D50. Also notably, and this is somewhat counterintuitive but consistent with theory, we see the maximum grain sizes at some sites increasing, probably due to effects of the lower median and grain size and the increased sand, allowing more competency to move some of the bigger material downstream. Using the morphodynamic mapping work I completed, we can see where these indications of channel aggradation sit, which are also ending at about that river kilometer 55 mark, and how the channel width has changed along the river. We see major increases in the channel width quite systematically, and that these are decreasing through time with just a couple of time steps we have. And there also maybe, I'm a little less convinced about this, a bit of a shift in the pattern of channel widening around that river kilometer 55 point. What this overall looks like to me is a diffusive sediment wave. This is what I went looking for when I started this project and investigation, where we have the most intense aggradation closest to the landslide, and then just a diffusive front moving some of that material downstream. It wasn't the whole story though, and that I think is why this case study is important and transferable. We go downstream, a different grain size class of material is creating a huge impact on the channel. So this is in that lower gradient reach where the river is narrower and diked, and the channel has filled with a massive quantity of kind of coarse sand granule-sized material that's been transported, we believe, in suspension through the steeper upper reach. It hits this lower gradient reach, drops on the bed, and is filling the channel. Repeat survey of the channel shows systematic aggradation values on the order of 0.5 meter to 1.5 meters, with particular zones of aggradation upstream of hydraulic pinch points in sort of sedimentation zones. The material is filling the channel, is reducing the hydraulic capacity of the channel within the dikes to convey the flow, and that has a very large impact on the timing of dike overtopping along the river, with implications for flood hazards. This plot here shows some of the timing of the aggradation. You can see the rating curves shown in blue and green are all prior to the landslide event, and they plot basically on top of each other. Then shortly after the landslide, we can see almost an immediate bed response in this downstream reach as it starts to aggrade, and aggrades at the site of this gauging station by about a meter over the subsequent 2 to 4 years. That really rapid response to a sediment injection a long ways away, some 50 kilometers upstream of where this gauge site is something that should give channel managers where landslides of this sort are a possibility pause in thinking about the assumption that they'll have a long time to respond to a diffusive sediment wave, when in fact, due to the sorting by grain size, we're getting a big impact rapidly far downstream. As a geomorphologist, I'm going to summarize with a sediment budget. We have a total volume of fluvially remobilized material between around 6 and 7.5 million cubic meters. That's a lot of material, but a relatively small fraction of the total slide deposit. So a lot of material remains available to the river to get picked up and moved down valley. Sediment smaller than medium sand accounts for about 30% of the slide mass. This material has been transported as wash load through the river to the river's delta and deep portions of Lillooet Lake where it was sequestered. It really does not influence the river's morphodynamics in a significant way. Coarse sand and granules account for about 40% of the slide mass. This material has interacted with the cobble bed through the braided reach, reducing the overall grain size distribution through there and dramatically increasing bed material transport rates, driving bank erosion and channel widening. We believe most of the actual volume of that sand, though, has been transported down into the diked reach, where the lower gradient downstream results in lower shear stress, and the sediment's transport capacity is reduced. Here, this coarse sand and granules become bed material load, probably transported both in suspension and as bed load. The downstream sediment transport capacity limitation has resulted in major bed aggradation through this reach, resulting in reduced capacity to convey flow of the river. Finally, cobble and gravel material represents about 25 to 30% of the slide mass and about 30% of the remobilized material. This has formed a sediment slug that is slowly dispersing downstream from the landslide, with the largest impacts in the areas closest to the slide, and the leading edge of impacts in 2017 interpreted to be about 25 kilometers downstream of the landslide around river kilometer 55. Changes associated with this coarse sediment slug moving through the river include substantial bed aggradation, probably on the order of 1 to 2 meters in many places, aggressive lateral channel migration and active channel expansion, along with formation of many new avulsion channels due to the aggradation. So thinking about the future, we can imagine that we've eroded out on the order of 7 million of 50 million cubic meters of sediment from the landslide. But based on analogs to other sites and kind of theoretical understanding of how rivers and landslide deposits evolve, we expect a kind of exponential decay pathway for the sediment remobilization out of the landslide deposit. If we use our one solid calibration point, I understand that that's pretty sketchy to do, but it's the data we have, we get a half-life estimate for this exponential decay pattern of about 28 years, and can use that to kind of forecast out the pattern of declining sediment yield through time from the landslide deposit. We can also, of course, look at, well, what if that estimate is wrong, and what's the variability in how this pattern may look? This is somewhat good news for the downstream sand impacted reach, as we expect the rate of mobilization of that material, where there's very high and fast connectivity to initial erosion out of the landslide deposit, to decline. And so the volume of that material entering that lower reach should be declining through time, and at some point we can hope that the capacity of the river to move it will exceed the delivery rate, and we'll be able to flush that granule to sand size material out of the channel and restore the hydraulic conveyance capacity without major, dredging sort of intervention. However, there's a bit of a problem in that the coarse gravel diffusive sediment wave may also ultimately enter that reach, and there we do not expect it to ever get flushed all the way down to the lake because of fundamental competence limitations due to the declining slope of the river channel. So with that, I'll close and say thank you for your interest, and invite you to reach out with questions, or if you just want to connect with me somehow, send me an email or connect on LinkedIn. Also, this last link here, bit.ly/Lillooet, will take you to the document that contains, it's an appendix to the main report, the geomorphic atlas I produced, where all of the data supporting the analysis that I shared here, lots of detailed and I think beautiful photos of the river system are included. So if it's a story you're really interested in, you can dig into the data there, and I'd love to chat with you more about it. Thanks much again, and hope you have a wonderful rest of your day.